All right, so now we're going to start our conversation on polygons. Um, we'll get eventually into more specific polygons, quadrilaterals, and then more specific quadrilaterals called parallelograms, and then even more specific parallelograms, rhombuses, squares, rectangles, and then some non-parallelograms like trapezoids and kites. But we got to know what a polygon is first. So, what is a polygon? A polygon is a closed figure in a plane. Okay, it means that there are no openings to it. There's no open-endedness to it, right? Everything's connected. But it's formed by connecting at least 3 line segments. Big key here is that they have to be line segments, endpoint to endpoint. So they have to connect endpoint to endpoint. Okay, you can't go endpoint to midpoint or whatever. With each segment intersecting exactly 2 others. All that has to be true in order to make this a polygon. If it's not formed by line segments, then it's not a polygon. If the segments are not connected endpoint to endpoint, then it's not going to be a polygon. And if each segment is intersecting more or fewer than 2 other segments, then it's not going to be a polygon. Those all are the requirements for making a polygon. Each line segment we call sides. Each endpoint where the sides meet is called a vertex. We kind of should know that at this point. A diagonal. The definition of a diagonal is a segment connecting 2 non-consecutive vertices. Okay? Consecutive vertices, consecutive sides and angles we'll talk about in just a second. But that's a diagonal, right? Or we can talk about consecutive vertices now. Consecutive vertices would be 2 vertices that share a side, right? So this vertex and this vertex share this side. So those are consecutive. This vertex and this vertex share this side, so those would be consecutive. Okay, but this is a diagonal because it's joining this guy, and they are not sharing a side. Now, you can draw more than one diagonal in a polygon, right? Here's a bunch of them. Here's a matter of fact, all of the diagonals in a pentagon, and we'll talk about that in a minute, but these are all the diagonals. You go from any vertex and draw a segment to any non-consecutive vertex. So from here to here and here to here would be 2 diagonals. Okay? Not just going, across a rectangle. Diagonals exist in other places as well. All right? Now, there are 2 types of polygons. There are convex polygons. A convex polygon is where no segment connecting 2 vertices is outside the polygon. And I'll show you what I'm talking about. In a convex polygon, consecutive vertices share a common side, consecutive sides share a common vertex, and consecutive angles share a common side. Okay? The other type is a concave polygon, and that's a polygon in which at least one segment connecting 2 vertices is outside the polygon. Now, here are examples of convex polygons. Okay? So what we mean by a segment connecting any 2 vertices, right? So take a segment and connect any 2 vertices. In this guy, there's a segment, I can take a segment from here to here and connect vertices. It's not outside, it's on that polygon. Or I can go from here to here, but I'm inside, I'm not outside. Or from here to here, I'm still all inside. As a matter of fact, no matter where you go, all those segments connecting the vertices are inside, or not outside. I don't want to say inside, not outside the polygon. Right? And that's true for all these guys. You can try it out. Connect your vertices, and none of those segments are going to be outside. That's convex. Concave are guys like this over here on the right-hand side. Okay? If you take a segment and connect it from, say, this vertex to this vertex, that travels outside the polygon. That's concave. Okay, and you see the other ones drawn there with the dotted lines. Another way to look at this is that concave polygons, it looks like some of the sides have caved in, right? Some of the sides are going into the polygon. A lot of different ways to tell. This segment joining vertices, if you can ever take a segment and join any two vertices, and that segment goes outside the polygon, it is concave. Okay? All right, let's try it out. Tell whether the figure is a polygon and whether it is convex or concave. Here's the first one. Is that a polygon or not? Here are the requirements. Must be made up of line segments, right? Are all of these line segments? Yeah, I think we can agree that they are. The line segments must be connected endpoint to endpoint. Depending on how you look at it, yes, all of these are connecting endpoint to endpoint. And last one is each segment must be joining exactly two other segments, right? If you look at this segment right here, it's joining 1, 2, 3 segments. It does not count. This is not a polygon. Okay, I don't want to hear you say, but that's two trapezoids, or there's two shapes stacked on top of each other. We are looking at this one entire shape. Okay? So it's not a polygon. It doesn't make a lot of sense to talk about convex or concave. We can try. Hopefully you're thinking this is concave because this side sort of caves in. In other words, I can take this vertex and draw a segment, and that segment's outside. So this would be considered concave if it were a polygon, but it is not. Okay? This guy is the polygon. Or is it all made up of line segments? Okay, they are. Is each segment connecting endpoint to endpoint? I think we can agree that they are. You can go around and look. Endpoint to endpoint. And then is each segment connecting, or each side touching exactly two other sides? This one I just drew is touching 1, 2. You can go around this all the way. 1, 2, 1, 2, right? And they are. They're all connecting exactly to other sides. So this is a polygon. Convex or concave, can you join any two vertices and have a segment go outside the polygon? I can try here, 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 here. Nope. Those are all inside. As a matter of fact, you can go around this if you want, but these are all going to be inside, and so this is going to be convex. None of the sides are kind of caving in. So this is convex. How about that guy? Is it a polygon? Made up of all line segments? Nope. This guy is not a line segment, so it's not a polygon. If you're asked why, you'd say that it's not made up of line segments. It's not entirely made up of line segments. Okay? Again, this one's tough to even talk about convex or concave. We can make a case for concave because you can join these two vertices and that segment's outside. Okay? Here, polygon or not? Made up of line segments? Each line segment connecting, or all the line segments connecting at endpoints? And the last requirement is that is each line segment touching exactly two others at endpoints? That's all yes. So this is a polygon. Convex or concave, I can join these two vertices with a segment that's outside the polygon, so it is concave. Okay? And that's how that works. Okay. If we have a polygon, we can classify those polygons in a lot of different ways. We can type them based on the number of sides, and you know a lot of these already. A polygon with 3 sides is a, triangle. A polygon with 4 sides. Do you remember? Quad means four, lateral means side, so quadrilateral is four-sided. 5 sides is a pentagon. 6 sides is a hexagon. 7 sides is a heptagon. 8 sides is an octagon. 9 sides is a nonagon. 10 sides, probably remember, is a decagon. 12 sides, this is the one that very few people remember. 12 sides is a dodecagon. And once we get outside of that number of sides, we kind of stop coming up with fancy names for them. So if it has more than 12 sides, and you notice we skip 11, there's not really a fancy name for an 11-sided polygon. But once we get past 12, we just use the number of sides with the suffix gon to call it whatever it is. So if it has 27 sides, then we call this thing a 27gon. So you know how many sides it has. Okay? So we're going to want to commit those to memory, because if I tell you that, you know, we have a heptagon, you need to know that has 7 sides. Okay? All right. Other ways to classify. Some polygons are equilateral. We know this at this point, that equilateral means that all the sides are congruent. If all the angles are congruent, we call that equiangular. And if it's both equilateral and equiangular, we've mentioned this before, we call that regular. It's a regular polygon. And again, things that you need to commit to memory. You need to know what it means for a polygon to be regular, that all the sides and all the angles are congruent. Okay? All right, classify some polygons. Classify this polygon by the number of sides and tell whether it's equilateral, equiangular, or regular. Explain your reasoning. First one. This is a polygon. We could go through the reasons why, but it is. Classified on the number of sides. Well, there's 1, 2, 3, 4, 5, 6 sides, which makes it a, you guessed it, hexagon. Is it equilateral, equiangular, or regular? Is it equilateral? Yes, all the sides are marked congruent. Is it equiangular? Yes, all the angles are marked congruent. So that means it is regular. All sides and angles are congruent. Okay? You'd want to write that out as you explaining your reasoning. This guy, 1, 2, 3, 4 sides makes it a quadrilateral. Are all the sides congruent? No, so it's not equilateral, so it can't be regular. Are all the angles congruent? No, it's not equiangular. So it's not any of these. And we just want to say something like not all sides are congruent. Not all sides, nor all angles are congruent. Okay? How about here? Take a second. See if you can figure out what this thing is. Okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. How many sides? 12 sides. What do you call that? It is a dodecagon. Is it equilateral? Yes, all the sides seem to be congruent. Is it equiangular? The answer to that question is no. If it's concave, it will not be equiangular. So equilateral, all sides are congruent. But not all angles. Like I said, the hint is if it's concave, it cannot be equiangular. Okay? So, there you go, how we're going to classify our polygons. Okay? Can use the idea of equilateral, equiangular, or regular. Here's another example here where we have a table that's shaped like a regular hexagon. Need to know what that means. The expressions shown represent side lengths of the hexagonal table. Find the length of a side. Well, all the sides are the same because it's regular. And if I want to find the length of one side, all I have to do is find x and plug that x in. So I can take these two guys and set them equal to each other. Subtract 3x, add 2, x is 8. Then, of course, I'd want to plug back in and find out what the side lengths are. So 3 times 8 plus 6 is 24 plus 6, which is 30 inches. The other guy, 4 times 8 minus 2. 4 times 8 is 32, minus 2 is 30 inches. They both suggest that the side lengths are 30 inches. Might be worth checking both, just to make sure you did it right. Okay? There you go. Okay, and this is section 1.6. You do have a worksheet out in Canvas. Make sure you have that done next time.